So in this video, I'll be discussing Einstein's coefficients, and it was Einstein who showed the interaction of radiation with the matter with the help of three processes, and we call them stimulated emission, absorption, spontaneous emission. And he showed that for a proper description of radiation with matter, the process of stimulated emission is essential. Uh, and let's talk about the stimulated emission first. Now, what's happening here is that an atom in the excited state is induced to return to the ground state, thereby resulting in two photons of same frequency and energy. And this process is called as stimulated emission. Now, this emission, the emitted photons move in the same direction and is highly directional in nature. The radiation is highly intense, it's monochromatic and coherent. The photons that are emitted, they are in phase, and there is a constant phase difference between the photons. Then the next important process is the spontaneous emission. In this process, the atom in the excited state returns to the ground state, and thereby emitting a photon without any external inducement. And this phenomenon is called spontaneous emission. And the emitted photons, in this case, they move in all directions and are random. The radiation is less intense and is incoherent. And the photons that are produced, they are not in same phase. And there is no constancy in the phase between the photons. There's another important point, that's population inversion. This population inversion, what it does basically, it creates a situation in which the number of atoms in higher energy state is more than that in the lower energy state. And usually at thermal equilibrium, the number of atoms, say, in the higher state, the population of atoms at higher energy state is much lesser than the population of the atoms in the lower energy state. And the phenomenon of making, if I have N2 number in the higher energy state and 1 number in lower energy state, so if I have N2 greater than that of N1, this is what is called as population inversion. And certainly there must be at least two energy levels where we can induce this population inversion, and there must be a source to supply this energy to the medium. The atoms must be continuously raised to the higher energy states, and we have those states where these excited atoms, they stay a little longer than that of the spontaneous process. And what we call this process is that you try to create a metastable state. Now, an atom can be excited. It can be excited to a high energy level by simply supplying energy to it. And normally, the excited atoms have short lifetime and release their energy in a matter of nanoseconds, and maybe of the order of 10 to the power of minus 8 to 10 to the power of minus 9 through spontaneous emission. That means atoms do not stay longer to be stimulated. And what we do here is we generate the population inverse, and this population inverse could be established. And once this population inversion is established, for that, what is necessary is that we have excited states, and they have a longer lifetime, a metastable state. And this metastable state is obtained in the crystals. And these levels lie in the forbidden gap of. In this video, I'll be talking about Einstein's coefficients and how Einstein's coefficients automatically lead to spontaneous emission of radiation. And it was probably Albert Einstein, and before the advent of the development of quantum theory of radiation, that it was possible to have statistical equilibrium between the radiation and matter. So if for the sake of argument I choose two energy states, say E1 and E2, and with N1 number of atoms in ground state and N2 number of atoms in excited states. Now, so uh, so the Einstein, what Einstein did, uh, he was able to show actually before the advent and the development of the quantum theory of radiation that it is possible to have some statistical equilibrium between the radiation and matter, only if there is a part from the induced emission which is proportional to the radiation density. And automatically the spontaneous emission which occurs even when there is no external radiation available. And this certainly was a genius idea that was put by Albert Einstein, and it was put forward by him to obtain a relation which certainly would determine the rate at which the spontaneous emission takes place. Now, considering the matter in equilibrium with the radiation, and assuming that the resultant radiation must obey Planck's black body radiation law. And what Einstein did, basically, he introduced the coefficients, and these coefficients are known as Einstein's coefficients. And these coefficients basically describe, what they do is they describe the induced emission, absorption, and spontaneous emission. So, induced emission, absorption, and spontaneous emission. And in order to achieve in order to get an idea regarding this spontaneous emission through Einstein's coefficients, what should we do is we'll consider two energy states. And what we have energy state 1 and we have energy state 2 of an atomic system, with corresponding energies as E1 and E2. And let's also assume that this N1 and N2 be the number of atoms per unit volume in these levels. I mean, level 1 and level 2, with the E2 equal to greater than E1. Now, what basically happens in absorption of the radiation is that an atom in the state 1, what it does, it gets it gets excited to the state 2 after absorption of radiation, and this process can occur only in the presence of radiation. So for absorption to take place, there's certainly the need of radiation, which will interact with the atoms in ground state, and can launch them to the higher energy states. And 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 in presence of radiation, we can what is also possible here is that we can already have the atoms in the excited state, and we can moderate the excited states of these atoms, and we can have stimulated emission of radiation, and at the same time we have the stimulated absorption of the radiation when the atoms in ground state, they attain some energy and they get excited to some higher energy states. Now, its rate on the energy density, if I assume that d omega is the energy density, we quote it as energy density, that's associated with the radiation field, of whose frequency, or I mean, whose angular frequency is E2 minus E1 by H cross. Now, if I choose d omega, what this d omega does, it gives the radiation energy per unit volume. This d omega within the frequency interval, we can think of the interval as omega and omega plus d omega. Now, the rate of absorption and the corresponding transitions from state 1 to state 2. So uh, we have two states, is obviously proportional to n1, as well as this d omega, this energy density that I was talking about. So what's going to happen here is that uh, that it's this n1 as well as this d omega will be proportional to the absorption per unit time. So if I choose that absorption per unit time as NAB, this is going to be equal to B12 and 1d of omega. And where this B12 is the coefficient of proportionality. Coefficient of proportionality. And now, when the atom is in excited state, I mean, it's in the state 2, it can make a transition to the lower state 1 through the emission of radiation. And in two different ways. I mean, in first one, what we call as the spontaneous emission. An atom in the excited state, it emits radiation even in the absence of the incident radiation, and so we can have spontaneous emission, and this spontaneous emission can happen even in the absence of electromagnetic radiation, and an atom in the excited state. Certainly, it's going into the ground state. Now the rate of this spontaneous emission that we have here is proportional to the number of atoms in the excited state. So we have n2 number of atoms here, and here we have n1 number of atoms in the ground state. So the rate of this spontaneous emission that we have, which I'll represent here as NSP, referring to the spontaneous emission per unit time per unit volume, is A21N2. So we have 1, we have 2 here. Now, in the second type of emission, so one emission which is spontaneous, which is completely plausible, and in this kind of emission, what we have spontaneous emission. Now, in the second type of emission, what's called as stimulated or induced emission, an incident signal that signal must be of some appropriate frequency, and what it does, it triggers the atom in an excited state to emit the radiation, and the rate of such radiation, the rate of such transition, I should say, to the lower energy state is proportional to the energy density of the radiation, of the frequency. What's the frequency is omega, as well as the number of atoms that are available in this N2 state, in the excited state. Hence, here what we have is the number of induced emissions per unit time, per unit volume. So let me represent that rate by N induced, and this is going to be equal to N2 B21 D of omega. So we have three kinds of things. One is rate of absorption, then we have the rate of spontaneous emission, and then we have the rate of induced emission. And the quantities that we have here, I mean, this B12, this A21, and B21, what they refer basically these quantities are the quantities that are related to absorption, spontaneous emission, and the stimulated emission or induced emission, respectively. And these coefficients, I mean, these quantities are called quantities are called as Einstein's coefficients, and they are actually determined by the atomic systems. Now, if we think about the thermal equilibrium, I mean, what we have N2, we have N1, we have E2, we have E1, and at equilibrium, what we expect is that the number of transitions from the lower state to the higher state must be equal to those from the higher state to the lower state. So how this can be compensated? This can be compensated by, so the point is at thermal equilibrium. At thermal equilibrium, what can we expect? We can expect that the rate for absorption is rate for spontaneous emission plus rate for induced emission. And we can substitute the right-hand sides of all the three equations for this equation. So let me call this equation 3 for the time being. And what I'll get N1 B12 T omega is N2 A21 plus N2 B21 T omega. And from this, what can I find? I can find this T omega. I can find this. So if I transfer this to this side, I will have N1 B12 minus N2 B21 T omega is N2 A21. So this T omega can be N2 A21 divided by N1 B12 minus N2 B21. And I can think of dividing numerator and denominator by N2. And what will I get out of that? So I will have this D omega will be A21 divided by N1 by N2 B12 minus B21. Now, if we can think of Boltzmann's law at this point of time, and what Boltzmann's law does, it can provide us the ratio of, we have two levels here, level 1 and level 2, and this Boltzmann law can correlate us the ratio of population of level 1 and level 2 at temperature T. And we can write down this Boltzmann's law, and we can write down this as N1 by N2 is e to the power of E2 minus E1 by KT. And K is the Boltzmann constant. And then this equation, we can think of rewriting this equation by making use of if we think of writing down this equation D omega, we can write it as D omega is A21 by B12 exp. I'm missing something here. This is N1 by, no, that's fine. So exp H cross omega by KT minus B21. So what we have done, we have used N1 by N2 from Boltzmann's law. And what we have obtained for D omega is A21 by B12 AXP. E2 minus E1 is H cross omega divided by KT minus B21. And according to Planck's law, I mean, the energy density of radiation at the thermal equilibrium can be written as, and we have the Planck's black body radiation law, and we can use the Planck's law. What it says is T omega, which is energy density, is H cross omega cube by pi square C cube times 1 by e to the power of H omega by KT minus 1. So what we can have here is we can think of comparing this equation and this equation. So if we compare this equation, say this is equation 5 and this is equation 6, and what appears to be the most important thing is we can immediately, this B12 must be equal to B21. if we compare these two equations, and that's quite clear that this B12 has to be equal to B21. So on comparing 5 and 6, so comparing 5 and 6, what we will have is we will have this B12 equal to B21, and when B12 is equal to B21, we can have A21 by B21 equals h cross omega cube by pi square c cube. So this thing, yeah, because we can compare it with A21 and B12, and that will correlate with h cross omega cube pi square c cube. And thus what we are able to find here is that the probabilities of absorption and induced emission, the two probabilities are same. There's no difference between the probability of absorption and the probability of emission. And if we can proceed from here, say for example, I mean, if I choose that, if I assume that there are n2 number of atoms per unit volume in the state n2, and dn2, and dn2 is the number of atoms undergoing, I have very bad handwriting, undergoing spontaneous emission in time, say in time tt. And then we can think of dn2 equals minus A21 n2 dt. And this certainly will lead us to the what we call as radioactive decay law. Radioactive decay law. So I can think of n2 equal to n2. Let me use some n2 at time t, n2 at time 0, e to the power of minus A21t. So from this equation, we can automatically estimate the mean lifetime of the state 2. This is the state 2 and this is the state 1. And certainly that mean lifetime of this state 2 is, if I symbolize that mean life by tau, this tau should be 1 by A21. Now we can subject this problem to the problem of hydrogen atom, and we understand the basic course of solving a hydrogen atom, and we can use the state P, the excited state of hydrogen atom, and the ground state of hydrogen atom, and subjecting our problem to hydrogen atom, we are able to calculate this A21 for hydrogen atom, and this A21 comes out to be 6 times 10 to the power of 8 seconds. So if we use the value of this A21 in the above equation, we can calculate this tau as 1 by 6 times 10 to the power of 8 seconds. So this value comes out to be 1.6 times 10 to the power of minus 9 seconds, which is basically the mean lifetime of this hydrogen atom to be in upper level, corresponding to a transition to P to 1s state. So spontaneous emission rate gives rise to the finite width of the spectral line, because this delta E is greater than this h cross by tau. So this is how the idea of spontaneous emission automatically comes out by exploiting the thermal equilibrium that's exploited by Albert Einstein. But at the same time, in practice, the observed widths are much larger due to other factors.
and they are larger due to Doppler broadening, collision broadenings, and so many other things.